Now that you know how to resolve forces, you can have much more complicated pulley connecting particle situations than you had in the first year. But basically what you're going to see, although this isn't like the only thing in the world, but the most common thing would be a slope and then something hanging down, or something sloped, which could be the same angle each side, or it could be different angles each side. So you've got an angle alpha there and an angle beta here, and then there's your pulley, and it is looking a bit like that. And we may or may not have to combine this with something about the coefficient of friction, because obviously we've got contact there, and we've got contact there, and we've got contact there. So if any of these aren't smooth, then we're going to have the friction considerations, thinking about the direction of friction and all that kind of thing. Same as when we looked at connected particles over a pulley, video 1, you could be asked about the force on the pulley. Now in this case, it's very, very similar to what we were talking about in the first one. You can just memorize it. It goes straight through the middle. And if this angle here is alpha, what you want to do is work out what that angle is and then halve it, because that's what this will be, half and half. So let's think what that would be. Well, the angles in a triangle add up to 180, but that's 90, so there's 90 between these two. So if I do 90 minus alpha, then I know what that angle is. And then if I halve it, then I will get this angle here and this angle here. Now, if we've got the more complicated scenario, where we've got two different angles and this double slope situation going on, it's just going to be the same idea though. What's that angle there? Well, the angles in a triangle add up to 180. So we do 180 minus these two added up, alpha add beta. And that's going to get you that angle. And then if you divide that by 2, then you'll find out what this angle here is, which is the angle between the two tensions that the resultant force will make, going straight through the middle. So that's an important calculation, finding theta. Once you've found theta, then it's going to be exactly the same as it was before, although it was a simpler calculation. The tension here is the same as the tension here. The tension here is the same as the tension here. And the resultant force will be 2t cos theta in both cases. 2t cos theta. And if you want to work out why this is the force on the pulley, then what you want to do is draw a line across here. That's 2 theta there, and muck about with the cosine rule. Or, easier than that, I'm going to do this in pencil and then rub it out. What you can do is resolve the tension in the direction of the resultant force. So you can say, okay, how much of this tension goes in that direction? So you form a right angled triangle, and then that angle in there is theta, and the hypotenuse is t. So adjacent, this bit here, is t cos theta. And then same thing with this one. Resolve the t force in the direction of the resultant force. The hypotenuse is t, the angle is theta. We are adjacent to the angle, and therefore the part of t in this direction is t cos theta. And there's 2 of them, and then the other bits of t, these bits, cancel out. And then what you get going down there is 2t cos theta. Probably easier just to remember it's 2t cos theta, to be honest, so long as you get your theta right, that it's bang in the middle of those two. Let's have a look at this problem here. We've got we're going to draw our 2 diagrams. So the first one is going to be on the slope. Always make your diagrams a decent size so that it's not too small and it's readable for you and the examiner. We've got a rough surface, and we know that the frictional force is half of the normal reaction. There's the normal reaction. We've got the tension in the string, and then we've got down here the weight, which is 2mg, but we're going to resolve that into these 2 directions. So in this direction, that angle there is this angle here, which is 30. So that's 30. So this is 2mg cos 30 into the plane, and 2mg sine 30 down the plane. So just your bog standard resolving the weight as we always have to do. This is going to be accelerating in this direction. Okay, we've got our other force diagram, because we're going to draw 2 separate force diagrams, and the other one is this one. And in our case, in this simple example, it's just hanging off the edge, so it's just going vertically, so you've got the tension in the string and the weight. And it's accelerating that way. So this is how we start our 2 force diagrams. Then for each of those, we're going to form equations of motion, and then we're going to do simultaneous equations. So we go down, we do our equations of motion. So we're going to get the sum of the forces is the mass times the acceleration. I'm going down as positive, so 3mg minus t is the mass times the acceleration. Okay, in this case, I'm trying to find the acceleration is what I'm interested in, so I'll make this say t equals. Okay, now this one. So I need to do the sum of the forces is the mass times the acceleration, and I'm going to be going up the slope is positive. So t minus a half r. Now, the trouble is, I don't know what r is, okay? So I've got a half r, and I don't know what r is. I've got to find that out. And then I've also got, so also negative, this 2mg sine 30. And sine 30 is a half. We could put sine 30. And then I'll replace it with a half. So we've got this little problem here, which we need to deal with, which is what is r, which is what we've been asked in part A. So we've got this kind of sub-problem, which is not the, like, connected particles, forces, Newton's second law, simultaneous equations, blah thing. This is a bit of an extra, and we do sometimes need to do these extra bits. And this is to find the frictional force. Not the frictional force, sorry, the normal reaction. Well, no, yes, to find the frictional force, which is the r, which is half of the normal reaction. So this is a little subplot in the exciting plot of this particular problem. So to find the normal reaction, I am going to do Newton's second law in this direction. The sum of the forces is the mass times the acceleration. I'm going to be going away from the plane as positive. So that's r minus 2mg cos 30 equals the mass 2m times the acceleration. In this direction, there is no acceleration. None at all. So this will be naught. So r will be 2mg cos 30, which is mg root 3. Don't forget, units. You don't want to be throwing a mark away here for not getting your units right. Okay, so there's that bit done. That was like part A, and even if they hadn't told me to do that in part A, I would have needed to do it to find the acceleration, because to find the acceleration, I need to do these simultaneous equations, and to do these simultaneous equations, I need to put the r in, and to get the r, I need to resolve that way. So even if you're not specifically told, you can work your way through the structure of the problem and see that that needs doing. Okay, this is r, so the frictional force is half of this. Okay, and I'm going to make this one say t equals as well. T equals, oh, what does this equal? The mass times the acceleration. Okay, so t is okay. So 2 force diagrams, equation of motion for each one, simultaneous equations. They're both equaling t. So I can bring these together. I'm going to do it over here like this. Now, as happens a lot, these m's are going to cancel. And then we can write it like this. And it's pretty easy to get it this far. Now, there's a common factor of g, so it'd be nice to pull that out. And it's not very nice having fractions in there, so we can pull out a half, but we must remember to change that to a 4. And that's a nice way to write it, but don't forget units. There's the acceleration. Okay, final thing, force on the pulley. We've got this scenario, so we're in this situation. So we know that the angle is going to be 90 minus 30, because this is 30 down there, this is 90, so it's going to be 90 minus 30, which is 60, and then halve it to get 30. So let's do this force on pulley over here. So the first thing we did was work out theta. And theta is 90 minus 30 all over 2, which is 30. So the force on the pulley is going to be 2t cos 30. So all we need to do is find out t. Do we know t? No, we don't. But if you've done simultaneous equations and you found one of the things, then you can find the other thing. Shall we sub a in here or shall we sub a in here? I think we'll sub a in this one. I think it's easier. So this is going to equal 2t. There's a now. Two t and then cos 30. Okay. Now, if you tidy this up, and I'm going to leave this as an exercise for you, write that down. I would recommend that you start off by using square brackets around here just to control it. And maybe put this root 3 over 2 at the front with that 2 so that they can cancel. And see if you can have a fiddle around and get it to look like this. 9 over 10 mg into 2 root 3 add 1. See if you can get it from there to there. So it's a good exercise in the sort of algebra you need to do in mechanics exams. Okay, so that is the force, and the units, don't forget, it's a force, so the units newtons.